All right, guys, we're going all the way back to the beginning, back to chapter 1, essentially, or chapter 0 even, before, we kind of got into a lot of what we're looking at now. So we're just going to spend the rest of the time from here on out reviewing as much as we can before we actually get to the AP test itself. So back at the very beginning, we were told that there are two types of data. Basically, there's categorical data and quantitative data. Our categorical data is going to be values of variables or individuals that can be expressed with words. So essentially, qualitative data, or it's also known as qualitative data, and it's just any kind of data that can be expressed with words or described using words. We also have quantitative data, which is any kind of data that is described using numbers or can be expressed with numbers, basically. So that's the difference between those two. Hopefully you remember that. When you graph on the AP test, we need to go over all the types of graphs that you might see. But when you give a graph on the AP test, whether that's to describe a normal distribution because you need to do that, or whatever it is that you need to list to draw a graph for, you need to make sure that you slut your graph. So you need to scale your axes, i.e. you need to make sure that they are reasonably scaled. In this case, we're going up by 200 each time, or we're moving from 180 days to 160, so on and so forth. But that's basically given in this problem right here. We also need to label our axes, so define what the y-axis represents or what the x-axis represents. We also need to name our units and title our graph as well. So all of that's, and they don't really title the graph. And then naming the units would just be making sure that you actually list these numbers right here, don't just actually scale it or put it to scale, but actually list what the numbers are or what the scale represents, basically. But you want to make sure that you include all of that. And our first type of graph that we're looking at here is just a bar chart, so it's fairly simple. Just a bunch of bars that's used to represent whatever data we find in our example here. We also have dot plots, and so in this example, the dot plot below shows the lengths of stays in days for all patients admitted to a rural hospital during the first week in January 2015. So each one of these dots basically represents one of those patients and whether or not they stayed for 0 days or 1 day, through 5 or 15, something along those lines, just for that month of January. So each one of the dots, they just represent a human, basically, in that sense. We also have histograms, and histograms look almost identical to bar charts. The only difference is that our bars are connected and there's no gap in between. So in this example, suppose that there are 2,200 seniors in a city's 6 high schools. 400 of the seniors are taking no AP classes, whereas 500 are taking 1, 900 are taking 2, 300 are taking 3, and 100 are taking 4. These data can be displaced in the following histograms. So really the difference between these two right here is that your first histogram represents a frequency histogram, whereas the second one represents a relative frequency histogram. So frequency histograms are basically going to go off of whatever numbers we were given in the problem itself. So I know that there were 400 seniors who took no AP classes, so my bar is going to go right around to that 400 mark, whereas there were 500 who took 1, 900 seniors who took 2, 300 who took 3. So our labels right here for our axes are essentially, or our units, our units represent more what the problem is actually looking for, and that's going to be a frequency histogram, whereas a relative frequency histogram is concerned mainly with the percentage of how many of those seniors took 0 AP classes. So there were about 18% who took 0, 23% who took 1, 41% who took 3, so on and so forth. So that's the difference between those two types of histograms. We also have a stem and leaf plot. So remember, what's on the left side of our line right here represents the stem. What's on the right side represents our leaf. When we're looking at this example, it says BPA is an industrial chemical that is found in many hard plastic bottles. Recent studies have shown a possible link between BPA exposure and childhood obesity. In one study of 27 elementary school children, urinary BPA levels in nanograms per milliliter were as follows, and it gives us all the numbers right here. Well, what we need to understand is that everything on the left side of the line represents what's on the left side of our decimal place right here. Everything that's on the right side of the line represents what's on the right side of our decimal. So 0 and 2 represents 0.2. or 0 and 8 represents 0.8, or 2 and 5 represents 2.5. Something along those lines. So yeah, you just need to understand how to read that stem and leaf plot, basically. We also have cumulative relative frequencies, which are, if we look, this is what a cumulative relative frequency graph is down here. If we look at this example, we'll notice that consider the essay grading policies of 3 teachers: Abrams, who gives very high scores; Brown, who gives equal number of low and high scores; and Connors, who gives very low scores. The histograms of the grades with 1 the highest score and 4 the lowest score are as follows. And this isn't necessarily a histogram, it's more of a, I guess, now that, yeah, that would represent a histogram, never mind, I'm sorry. But anyways, what we want to notice is that Abrams gives quite a few high scores right here. So a lot of his distribution, or a lot of his data, is going to rest right here in the 1 column, whereas it's going to kind of taper off down here to 4. Well, if you look at the cumulative relative frequency graph right here for Abrams, you'll notice that if this down here represents 0% and this represents 100%, you'll notice that that data really shoots up in this 1 column right here. So that data shoots up and then it kind of tapers off as you get to 2 and 3 to represent the full 100% of students right here, but it's going to shoot straight up right off the bat. When you're looking at Brown, it says Brown gives equal numbers of low and high scores, so Brown's going to have more of a normal distribution that's centered right around 2, okay? And so with Brown, what's going to happen is it's going to kind of evenly go up, but then once you hit 2 right here, it's going to shoot up on this cumulative relative frequency, and then it's going to kind of taper off for 3 and 4 right there. Whereas Connors gives a lot of low scores. So he's going to, a lot of his data is going to be in the 3 to 4 range right here. So Connors is going to have very little data, so it's going to, that curve's going to flatten right here from about 1 to 2, but when you hit 3, it's going to shoot up and then kind of taper off right around 4. So that's essentially how you would create a cumulative relative frequency graph or plot based on other data that you've been given for that. Okay. We also, when we're asked to describe distributions, we need to make sure that we cuss our distribution on the AP test. So we need to make sure that we list a measure of center, which is either the mean or the median. We need to list our measures of spread, which can be IQR, or interquartile range, or standard deviation. And we need to include our shape as well, which is normal, skewed, uniform, bimodal, etc. And then we also, before we get to that, we need to make sure that we know what shape represents what. So this would represent a symmetric shape. Bell-shaped can also be listed as a symmetric shape as well. This would represent something skewed to the right, so where a lot of our data is actually on the left, but it kind of tapers off on the right. That's representing a skewed to the right shape. Skewed to the left is the exact opposite, where most of our data is on the right, but we have some outliers here on the left that force the data to, force the distribution to be skewed. So that would be skewed to the left, and then uniform would look something just like a straight line across. Okay, the last part of CUS, basically, or the U part, so the C represents center, S represents spread, S represents shape. The U part right here represents kind of unusual features, basically. And so those are outliers, clusters, or gaps. In this example, we're given this graph right here, okay? And simply saying that the average age at diagnosis, so the example is Hodgkin's lymphoma is a cancer of the lymphatic system, the system that drains excess fluid from the blood and protects it against infection. Consider the following histogram. We're given this histogram, and so simply saying that the average age at diagnosis for female cases is clearly around 50, which would represent kind of the center of this distribution, really misses the point. Instead, what we would say is that the distribution of ages at diagnoses for female cases of Hodgkin's lymphoma is bimodal, because it has 2 peaks right here, bimodal, with 2 distinct clusters that are centered around 25 right here and 75 right here. So that's really what we want to describe. Not necessarily that this is a normal distribution, but more the shape that is bimodal, And I mean, I would say that you could probably get away with saying that there's a center at 50, but you would also want to note that the center of each peak for this bimodal distribution lies about 25 and 75 as well. Okay, so just to kind of summarize all of this up, we want to make sure there are 3 keys to describing a distribution. That's shape, center, and spread. And then if there are any outliers or clusters or gaps, anything like that, you want to also list that as well. And then you also want to provide context when you describe those distributions as well. Just context from the problem itself is going to be best in this case. You also want to look for reasons behind any unusual features. So why is it that you see an outlier somewhere or anything like that? You want to kind of be able to understand and describe that. A few common shapes arise from symmetric, skewed to the right, skewed to the left, bell-shaped, and uniform distribution. So you just want to make sure that you list whatever shape you can. Like I said, bell-shaped and symmetric are basically identical. So you can say one or the other, but then you also want to make sure that you say, if it is skewed, say it's skewed to the right or skewed to the left. For categorical or qualitative data, or data that you can describe with words, dot plots and bar charts give useful displays, whereas quantitative data should be described with histograms or cumulative relative frequency plots or stem plots. Those are going to give useful displays for quantitative, whereas bar charts and dot plots would be good for categorical data. And then in a histogram, relative area corresponds to relative frequency in this case.